All right, so hello everyone. I'm Norman Wahlberger, and today we're going to carry on talking about these three very important French geometers, Meusnier, Monge, and Dupin. So we talked about Monge last time, and today we're going to concentrate on Charles Dupin, who lived from 1784 to 1873. And he was actually a student of Monge. So Monge was a very important teacher, and one of his major achievements was to establish the École Polytechnique, which is a very important French school. And he and Carnot basically set up this university, which became very prestigious. And it was really a key point, I suppose, in the history of education, history of higher education, because it was one of the first universities that was really oriented towards accepting people on merit rather than on aristocratic credentials. This was the outcome of the spirit of the French Revolution. They had just chopped off the heads of a lot of the nobility. There was this feeling of democracy and inclusiveness, and so they wanted to open up the educational system to the broader masses and get people in there who were really the best, not just the most socially advantageous. So Monge was a very important teacher, and Dupin was one of his star students. And he was also in the military tradition of these other fellows. He was a naval engineer, and also became good friends with Napoleon, and became a senator in the Napoleonic times. His contributions were quite interesting, and I'm going to start with talking about an explanation of a diagram that we talked about last time. We were talking about the lines of curvature for an ellipsoid. So here's an ellipsoid again, and we had lines of curvature, well, maybe with regard to these four umbilical points. Something like this. And then there were, other ones kind of went around like this. Okay. So we have some kind of story like this for the lines of curvature of an ellipsoid. And I remind you that the lines of curvature are just the lines on the surface, which at every point are going in the principal directions. Okay? So at every point, we're talking about the two directions, principal directions, where the curvatures are maximum and minimum. So those are the curvatures we're usually calling little k1 and little k2. Okay, now Dupin discovered a remarkable connection between the lines of curvature and the system of triply orthogonal coordinates in space. So Dupin realized that there was an intimate connection between these and a particular triply orthogonal coordinate system. Now what does that mean? Well, it means a system of surfaces. So that means, i.e., three families of surfaces which meet everywhere orthogonally. So one example, of course, is just planes which are parallel to the coordinate planes. One family of planes in the xy direction, another in the xz direction, and another in the yz direction. So those three families of planes have the property that whenever three of them meet, they do so orthogonally. But there are other interesting examples, just as in the planar case, there are other interesting examples. And we talked about an example last time where we had confocal conics in the plane, and they had the property of being a doubly orthogonal system in the plane. So the idea is how to generalize that kind of thing to the three-dimensional story, and Dupin figured out how that goes. And it's a very beautiful story, and it actually has some real-life applications to physics and some electrodynamics, I believe. Okay, so how does that go? So maybe I'll draw it here. So Dupin realized that there was another two families of surfaces, and we can perhaps draw them. If I take just one of these lines of curvature, say that one there, and it'll have an opposite one on the bottom. And you should think of this as, it'll be a little bit rounded like this. You should think of this as being part of, or a cross section of a hyperboloid of one sheet. Okay, that comes and meets this ellipsoid exactly in this line of curvature and the opposite one in the bottom. Okay, and then there's also some hyperboloids of two sheets, which are, say we choose one of these ones, maybe this one here. Okay. So then there's a hyperboloid of two sheets, which it's like a hyperboloid in this direction and also another one in this direction. Okay. So the first one is a hyperboloid of one sheet, comes in and meets the ellipsoid along these red lines of curvature, and the other family, one of which is this blue hyperboloid of two sheets. And Dupin realized that these are actually mutually orthogonal. They're meeting orthogonally. And they're just one of, they each belong to families, so there are three families of such surfaces that are everywhere mutually orthogonal. So whenever three of them meet, they do so orthogonally. And it's very pleasant to write down the algebraic description of such things. So let's do that. Okay, so that's going to be a motivating picture. And now a bit of algebra to describe things explicitly. So we're going to look at, consider quadrics of the form x squared over a squared minus lambda plus y squared over b squared minus lambda plus z squared over c squared minus lambda equals 1. And we'll agree that these numbers a, b, and c are arranged in ascending order. So a squared is less than b squared is less than c squared. And lambda is a parameter. So if lambda is 0, then we get an ellipsoid. But if lambda has other values, then, well, different things can happen. So if lambda is less than a squared, then we get an ellipsoid. While if lambda is between a squared and b squared, then, well, this will be a negative. There'll be a negative sign coming here, but these ones will be positive, and we'll get a hyperboloid of one sheet. So that's like this kind of thing. That's a rule surface. And if lambda is between b squared and c squared, so that there's two negatives and one positive, then we get a hyperboloid of 2 sheets. And if lambda happens to be bigger than c squared, well, then there's all these negative terms, and then the quadric is imaginary. There aren't any points on it. All right, so for a given x, y, z, for a given point x, y, z in space, if we think about solving for lambda, so we think of a, b, and c as being fixed and ask which values of lambda will give us surface which lie on or pass through this point. So for given such value, this is a cubic equation in lambda. And it turns out that it has always 3 real roots, okay, or 3 approximate rational roots. Depending on your orient. No, we don't need to put quotes on that because that's real. So it has 3 real roots or 3 approximate rational roots. And so there's, the fact then is, maybe we can write it here. So theorem that through every point in space, there are approximately, or maybe I should say, there are 3 quadrics of this kind. So for every point, say P, there are 3 quadrics of the form star that, say, approximately pass through P. And when you actually look at the 3 roots of this cubic, then you'll see that one of them is of this kind, and one of them is this kind, and one of them is this kind. So there are 3 quadrics that approximately pass through P. One is an ellipse, or an ellipsoid. One a hyperboloid of 1 sheet, and one a hyperboloid of 2 sheets. So this picture here is quite general, and we can choose any point in space. We can find 3 in this family that pass through that point. And they're all mutually orthogonal. And they're all mutually orthogonal at P. Let me convince you of that mutual orthogonality aspect. So this is the equation that we're considering. So the tangent plane at P, let's make it point x0, y0, z0 to be specific, to the quadric star that we just rubbed off, has equation x times x0 over a squared minus lambda plus y times y0 over b squared minus lambda plus z times z0 over c squared minus lambda equals 1. So this is a relatively easy computation. You can either do it by calculus, by calculating the tangent plane, or more conceptually, you can do a bit of projective geometry and write down the matrix for this quadric. It's going to be a 4 by 4 matrix. And then on one side, you plug in the projective point x0, y0, z0, 1. Take the transpose and multiply it on that side, and then you multiply it out, and you get the equation of this tangent plane. Notice that the equation is a kind of a polarization of the actual identity itself. That if x happened to be x0, then you would just get the equation of the plane at the point x0, y0, z0. It's a kind of a bilinear version of the quadratic equation of the quadric itself. All right, so that's the tangent plane, and its normal then is a plane in x. Its normal is just the vector whose coordinates are x0 over a squared minus lambda, y0 over b squared minus lambda, and z0 over c squared minus lambda. So if we have two such different tangent planes for different values of lambda, say lambda 1 and lambda 2, so two such tangent planes have normals with a dot product or inner product so if I take the dot product of one of these vectors with another one exactly the same kind, I'll get an x0 squared, and I will have a squared minus lambda 1 times a squared minus lambda 2. And then a corresponding y0 squared over b squared minus lambda 1, b squared minus lambda 2, plus z0 squared over c squared minus lambda 1, c squared minus lambda 2. We'd like to convince ourselves that that's going to be 0. That's the statement that if these two tangent planes meet at x0, y0, z0, then their two normals are going to be perpendicular. So why should this thing be 0? Well, because of the pleasant identity that we can write this, I think there'll be a factor of lambda 2 minus lambda 1, but aside from that, I can write it as x0 squared times 1 over a squared minus lambda 1 minus 1 over a squared minus lambda 2. Okay, and then there are exactly three other terms exactly following the same pattern. Okay, so why is this? Because this is sort of decomposition partial fraction, so if we put this over a common denominator, we get this thing here, and then the a squared minus lambda 2 and the a squared minus lambda 1, the difference will be just minus lambda 2 plus lambda 1, so I guess it's lambda 1. I should put lambda 1 minus lambda 2 here. So if I cancel that factor there, then I'm just getting this. And then this is 0 because we're assuming that x0, y0, z0 lies on both of these quadrics. So the x0 squared times this first term plus the y0 squared times the corresponding 1 over b squared minus lambda 1 plus the z0 squared over 1 over c squared minus lambda 1 will be 0 because we're assuming that the point lies on the quadric. And similarly for the second term, because it lies on the second quadric too, we're assuming these two quadrics meet at this point x0, y0, z0. All right, so that's the reason why the dot products are 0, and these things are actually really perpendicular where they meet. So we've really just established this theorem, which I might write down here. So the theorem that we've essentially established is that the quadrics of a confocal system are mutually or form a triply orthogonal system. Okay, why are these things called confocal system? Well, if you take the quadric, x squared a squared minus lambda plus y squared b squared minus lambda plus z squared c squared minus lambda equals 1, and you say meet it with one of the coordinate axes, or coordinate planes, say set z equal to 0, then you're getting two conics that lie in the plane that have this form, and it's well known that that's a way of describing the conics in a confocal system in the plane. So if you remind yourself of the formulas for the foci of a conic when it's written in this form, then you can see that take the difference of these things and it won't depend on lambda, so that any such conic has the same foci. And that's going to be true not just if you set z equals 0, but also if you set y equals 0 and set x equals 0. So in each one of the coordinate planes, you're getting this family of confocal conics, but with different foci in each of the three different coordinate planes. And now we come to the lovely theorem of Dupin. I mean, Dupin would have worked all this out. And then the culminating theorem is the following. That the surfaces of any triply orthogonal system meet in the lines of curvature. So this is a very general statement. So that whenever you have a triply orthogonal system of surfaces, one family of surfaces, another family of surfaces, another family of surfaces, so that whenever they meet, we have orthogonality between the three surfaces at that point. Then necessarily, if you look at any one of those surfaces and look at where the other elements in the family meet it, the lines of intersection where the other two families are meeting that one surface are going to be lines of curvature of that surface. In particular, the lines of curvature of the ellipsoid are exactly where these hyperboloids of one sheet and two sheets intersect the ellipsoid. So as a particular case, so the lines of curvature of an ellipsoid are just the meets with the other two hyperboloids in the triply orthogonal system to which the ellipsoid belongs. But just as well, This also gives us information about the lines of curvature on the hyperboloids. So just equally, if we were interested in this hyperboloid of one sheet, for example, and what are its lines of curvature, then again, what we're just doing is we're taking the other two families in the same system, namely the ellipsoids and the hyperboloids of two sheets, and meeting them in with this hyperboloid. That's how you get the lines of curvature for the hyperboloid of one sheet or of two sheet. So really lovely stuff, I think. All right, so Dupin, of course, was also famous for a number of other things. And one of those is really a discussion of this indicatrix that I've mentioned before earlier in this lectures. And that's really very closely connected to this idea of normal paraboloid of a surface. So if we have a surface, S, surface, and we have some point on it, and we've seen the usefulness of thinking about, first of all, the tangent plane, of course, and then the second quadratic approximation, this normal paraboloid. So of the various quadratic approximations, the normal paraboloid is particularly important. So this is the normal paraboloid, and it's a paraboloid that has its axis perpendicular to the tangent plane. So we're calling the normal paraboloid. And this is really useful for us, this normal paraboloid, because, well, questions of curvature of the surface can be reduced at the point P to questions of curvature of this normal paraboloid. The paraboloid being just a quadric means that computations for it are a lot simpler. So that's been our sort of guiding philosophy in our discussion of curvature. And really this goes back to Dupin at least, because he was very interested in this normal paraboloid, and he studied what's called this indicatrix. He said, well, one way of thinking about this normal paraboloid or visualizing it is to slice it with a plane, not actually the tangent plane, but something that's parallel to the tangent plane, but just a little bit away from it. Okay, so we slice the same paraboloid, normal paraboloid, with this, this slightly removed plane, and we're getting then well, in this case, an ellipse, or if we're dealing with a hyperboloid, it would be actually a hyperbola. And this elliptic cross-section, is what's called the Dupin indicatrix. The Dupin indicatrix of the surface S at P. So it's really a slice of the normal paraboloid that's approximating S at P. And what did Dupin use this for? So Dupin used the indicatrix as a sort of a quick, almost a visual indicator of curvature in any direction, of, well, normal curvature, normal sectional curvature. In any direction at P. And so probably I should remind you of the fact that we've mentioned many times already, but it's probably a good idea to do it again. So recall that if you just have an ordinary parabola, very fundamental fact, we have a parabola 2z equals, not 2y, say, equals ax squared, just in the xy plane. Okay, so normalize that way. Then the curvature, little k, is a. That's the curvature at the origin. That's how much curvature there is at the origin. And in terms of this diagram that I discussed last time, if we sort of slice at some level, it doesn't have to necessarily be the level 1. It would be convenient if it was up 1 unit, but it doesn't have to be. If we think of this little triangle here, so that's x and that's y, then we can sort of rewrite this by saying that a equals, well, 2y over x squared. And so the quadratic curvature, k, which is little k squared, is a squared. It's going to be 4, maybe we call this r and this q perhaps. I can't remember last time. So 4 y squared, which will be q, and the quadrant's q, and x squared, which is r. But in particular, if we're holding this y value fixed, which is sort of what we're doing when we're looking at this indicatrix, so if the y value, y or q, is fixed, then the curvature is proportional, the quadratic curvature is proportional to 1 over the quadrants here. Okay? Or if we're just talking about the curvature itself, the little curvature, the curvature is proportional to the radius, to 1 over the radius in this direction. No, maybe I should write is proportional to 1 over x, because r is just x squared. Or to put it another way, x is proportional to 1 over the little curvature, which is the radius of curvature. Radius of curvature. Let me check that I have that right. Oh, there's an x squared here. So there's an x squared. Oh, there was an r squared here. Yes, sorry, I made a mistake. There's an x squared here. And so there has to be an r squared here if I'm squaring everything. So let me just correct this. So if y or q is fixed, then capital K is proportional to 1 over r squared. So k itself is proportional to 1 over x squared. Or x squared is proportional to 1 over k, which is the radius of curvature. And this is the way that Dupin would have thought about it, that basically the quantity x squared and the radius of curvature are proportional. And it doesn't matter what height we're at in this Dupin indicatrix. That's the beauty of it. So if we go back to this indicatrix story, if we have some surface and we have its, let me write its normal paraboloid like this, and here is the Dupin indicatrix right here. Then if you're going in a certain direction at the point, let's say you're interested in the curvature in a particular direction, Dupin just says, well, just have a look at the ellipse. This is an ellipse up here. Just go in that direction and see how far you have to go. The square of that distance, or in other words, the quadrants, this quadrant is proportional to the radius of the curvature in that direction. So that's playing the role of the x there. Okay, so you have this ellipse, and you can see how far the ellipse extends in different directions, and the extents in the different directions are just telling you are proportional to the actual radii of curvature of the actual surface at this point. So the indicatrix is a very good word because it's a sort of a visual graphic thing that contains all the information of all the curvatures in all the directions at this point P. So this whole, the emphasis that I've had in my development of curvature has very much been towards the normal paraboloid, and we see that really the ideas go back to Dupin at least, that this is a very natural thing. He was obviously very aware of the importance of this parabolic approximation to the surface because that's what he used to calculate this indicatrix. So it's good if one connects with something that's historical. All right, Dupin was actually interested in another very pleasant topic, which has to do with conjugate directions. And it's not studied that much these days, but it's actually a classical subject in the geometry of conics that goes back to Apollonius. So I will draw things in terms of an ellipse, but one could also make the same analysis for a hyperbola. So if you have an ellipse in the plane, there is a notion of what a conjugate diameter is. So the ellipse has a center, of course, and any line through the center is called a diameter. Okay, that's a diameter, and Apollonius realized that there was a kind of an involution on diameters. And the way Apollonius thought about it was that if you take all the secant lines which are parallel to this given diameter, and you take all their midpoints, the midpoint of this is going to be this, but if you take all the midpoints of all of these things, all the midpoints, then those midpoints lie on a line. And furthermore, that line is parallel to the tangent of the ellipse at the original diameter that you started with. And moreover, if you play the same game with this diameter, the red one, you take lines that are parallel to it, another secants, and you take the midpoints of them. So you take this midpoint, and you take this midpoint, and so on, then you get the diameter you started with. Okay, so I could say that so secants parallel to a given diameter have midpoints lying on the conjugate diameter. So if we started with a diameter, say, call it D, then this other conjugate diameter, we could maybe call it D prime. Okay. And this is, so if we started with D, then we end up with D prime. And this is an involution in the sense that I've said that it's completely reversible. An involution. And these secants parallel to a given diameter have midpoints lying on the conjugate diameter d prime, which is also parallel to the tangent of the conic at the place where the diameter meets it, at the points where D meets it. All right, let's do a little calculation, see what it looks like in coordinates. Always instructive. So suppose that we have an ellipse. Let's say the ellipse, so it's got to be a central ellipse, so we'll put the origin at the center. So we'll write it as ax squared plus 2bxy plus cy squared equals 1. So a rather general form for an ellipse. So it could be at some angle. Okay, so there it is there. Origin's there. It's got a center there, and we'll choose some point on it, say RS. It's a point on this ellipse. How do we calculate the tangent? That's sort of what we're doing. Well, let's just use a little bit of projective geometry just for fun. So we'll write down the matrix for the conic. Conic is associated with a matrix, and in projective coordinates, so A, B, B, C, and then there'll be a -1. Because remember, in introducing projective coordinates, we have to introduce a Z, and so that 1 will get replaced with the Z squared. And then you bring it to the other side, it's actually a -z squared. So that's the matrix. And this point here projectively corresponds to the homogeneous triple RS1. And so to get the tangent, we just multiply the matrix by the transpose of this thing. So we're just going to take A, B, B, C, 0, 0, -1, 0, 0, and multiply by the transpose RS1. And what do we get? We get A times R plus B times S, and then B times R plus C times S, and a -1. And that really corresponds to then a line, and the line has equation. It will go up here. So we get the tangent has equation AR plus BS times X plus BR plus CS times Y -1 equals 0. Okay, so that's the tangent line, and its normal is just the vector this comma this, and a direction vector for it. So to get a direction vector, we just rotate the normal vector by 90 degrees. Okay, the way we rotate by 90 degrees is we take the first term, BR plus CS, and then the second term with a minus sign, minus AR minus BS. So there's a direction vector for the tangent. So that's the vector there that I've just computed. Okay, and that's going to be then the conjugate direction. Okay, so the conjugate, so there's one diameter that we're starting with, the diameter to RS, and then the conjugate direction is going to be parallel to this thing here, so it's going to be in the direction of this vector V. V doesn't necessarily have to lie on the ellipse because we haven't normalized it yet. So there's really a transformation from going from RS to this vector V. What we're really doing is V as a linear function of RS. If we just started with RS, we would have to multiply by the matrix B C minus A minus B. So this matrix, which is related to this one, of course, but not in an entirely obvious way, this matrix is performing this conjugation involution on the diameters. Okay, I might give you a problem to do. So as a problem, you can check that if we look at the special case, so for the special case of an ellipse just sort of in rectangular form, x squared over a squared plus y squared over b squared equals 1. So if RS lies on the ellipse, show that a conjugate point is a conjugate point on the ellipse is S A over B, comma, R B over A. Okay, so we're talking about an ellipse sort of in standard position with its principal axes in the x and y directions, and now we're choosing some point RS, and we're trying to find this conjugate direction. And the conjugate direction is given, there's the point there on it is S A over B, R B over A. Okay, so what did Dupin do with these concepts? Well, first of all, he used since he has complete control over the curvature in terms of a normal section and the indicatrix, he's easily able to show that it turns out that the curvature in one of these conjugate directions of a surface and the curvature in the other conjugate direction are related. And the theorem is that, so again, Dupin, the sum of the radii of curvatures in conjugate directions is constant. And I'll just give you a proof in the special case of just using this problem where we've already calculated what the conjugate is there. So in the special case, once we know a point RS on the indicatrix, so using the indicatrix, and the fact that we've established earlier that the radii of curvature is proportional to the square of the displacement to the ellipse. And previous result, we need show that if you take this quadrant from that r squared plus s squared, that's proportional to one of the radii of curvature. And here's this other point that's, say, S A over B and R B over A. So we also have to take this quadrant. So we have to add S A over B squared plus R B over A squared. Now hopefully that's all constant. No, maybe no, let me do it separately. Let's add the r things. So there's an r squared here and an r squared times b squared over a squared. So altogether that's r squared times a squared plus b squared all over a squared. And then if we add the s things, we get s squared times, okay, there's an a squared here, and then there's going to be a b squared coming from there, so a squared plus b squared all over b squared. Okay, and pleasantly there's an a squared plus b squared factor that comes out. And once we take that out, with this r squared over a squared plus s squared over b squared, and r and s are points on the ellipse, so that's equal to 1. So there's no rs dependence, it's just a squared plus b squared independent of the point rs that you're starting on. And I have to mention one more theorem of Dupin, which is very much in the same direction as the conjugate, relates to these conjugate directions, and it's really a motivating reason for some of this discussion, which is the following theorem. So you have a surface. Okay, here's some surface S, and here's some point P. Okay, and we have this normal paraboloid that's approximating things at P. So what happens, let's say we choose in the tangent plane, we choose a certain direction. And we look at tangent planes in that direction. So we're looking at a curve in the plane. Maybe I'll draw it like this, a curve in the plane that's in that direction. And at each one of these points, we're looking at the tangent plane. So let's look at a nearby point and look at its tangent plane. Okay, because Dupin was a student of Monge, he would have thought, okay, these are almost adjacent points. The natural thing to do if you have two adjacent points on a curve is to find the intersections of those two those two tangent planes. And those two tangent planes, the one at P and the one at this point Q, they're going to meet in a line. All right, so the tangent planes at Q and P meet in a line, L, and that line L will be a line in the tangent plane. And so what he says is if we choose one direction, then we get another direction. Okay, so we start, this is the input direction, and this is the output direction. And the theorem of Dupin is that these are conjugate directions. These are conjugate directions, well, with respect to the paraboloid. And that basically means with respect to to any one of its indicatrices, with respect to the paraboloid, or i.e., or its indicatrix. All right, I better stop there. So that's good. So that's a very important sort of chapter in French geometry. And in our next lecture, we're going to move to Germany and the great Gauss and start talking about some of his very important contributions. Thanks. Yeah.